Well, this is a dedicated bunch of scientists. Yeah, no rain is going to stop us. Not a little bit of rain, not with the promise of the sun to come. Yeah. Yep. So as before, the School of Physics and Astronomy. I'm Jim. How many people are here for the first time? God, I can't believe this. Okay, great, awesome. Thank you. Thank you very much. So then let me introduce myself. I'm Jim Kekelius. I am the head of the School of Physics and Astronomy. And on behalf of the school and the Minnesota Institute of Astrophysics, I welcome you to a summer of astounding astrophysics. Our speaker today is Professor Lindsay Glesener. She actually comes from just outside of Duluth. I don't think you had that much to do with it, but okay. Anyway, okay. But then she got her bachelor's in San Francisco and got her master's and PhD at Berkeley. And having had enough of those California winters, came here, where she's been a professor ever since. She's a McKnight Land-Grant Assistant Professor. She's an Associate Professor now. National Science Foundation Career Award winner. And she concentrates on the sun's remarkable capabilities for accelerating particles. And she will tell you all about this. I will tell you about the sun. Because she's going to talk about all the stuff that's coming out of the sun. And I just want to talk about the stuff that's inside the sun. Probably know 93 million miles from Earth. Okay. It has a mass about 330 times that of Earth, with a radius of nearly 110 times that of Earth's. The center of the sun is 27 million degrees Fahrenheit. Yes, exactly. It cools off slightly to 11,000 degrees by the surface, 11,000 degrees Fahrenheit. Inside the sun, the source of the power, the source of the energy that comes out is the fusion of deuterium nuclei into helium nuclei. And the helium nucleus is just a little bit lighter than the two deuterium nuclei. And since E equals mc squared, that small difference in mass produces a large amount of energy. And a lot of protons get used up inside the sun, 600 million tons per second. Okay. So I think we have until it runs out. And one thing that I think is pretty remarkable is that the mass of the helium nucleus is 0.9936 that of the two deuterium nuclei. If it was 0.9946, the outflow of energy would be too slow to form the elements. We wouldn't be here. If it was 0.9926, they would fuse too fast and wouldn't have a chance to form stars. So it is just right. The light, so the charged particles are created in this fusion. They move, they get scattered. And as I mentioned on my talk, acceleration is not just speeding up or slowing down, it's any change in motion. So every time it accelerates, it emits light. The light created in the center of the sun takes a bit of a while to make it to the surface, about 40,000 years. So the light we're seeing now is aged in the wood. And then it takes 8.5 minutes to get to us. So with all of that, now I'm ready for questions. No, okay. And now, Lindsay, take it away.
Okay, let me test the mic first. Does it work? Yeah?
Yes.
People in the back are happy? People in the front are happy? Okay, we're good. Wait, 96 million miles away sounds like a pretty long distance, but in astronomical terms, this is really not much. And in fact, I think a lot of the message of my talk is kind of like, the sun affects us because it's in our backyard Or if I were to say that completely accurately, we are in the sun's backyard. And as we're going to see, that means there's a lot of things that happen at the sun that have a big effect on us. So why don't I go ahead and dive in, and I'll also just start by repeating Jim's thank you very much for attending. It's great to see so many people show up. Hope you enjoy it. I'd love to chat with you afterwards if you have more questions. Okay, that's my title slide. Since we're on my title slide, I'd like you to look at this picture of the sun. It might not look like you're used to seeing it, and that's because I believe that everyone in this room usually looks at the sun using visual wavelengths that you can see with your eyes or maybe a telescope. That's not this. These are ultraviolet and X-rays. And then we've chosen some colors, some false color that we can see just in order to make this beautiful image. But this is what the sun looks like in ultraviolet and X-rays. Okay, so what do we know about the sun? I think that everybody is already familiar with the fact that the sun showers us with the light, the energy, the warmth that we need to survive. We're all pretty big fans of the sun. But what is it like living in the sun's backyard? Well, the sun can also be pretty moody. It can lash out at us. And those lashing outs take the form of bright bursts of radiation from the sun. We call those solar flares. And they also take the form of the sun throwing out vast masses of plasma at us. And sometimes that happens. It's actually been happening a lot the last couple of years because we're in a time that is a particularly active time for solar activity. This video is actually a set of composite videos from various NASA spacecraft so that we can see the sun as it's producing one of these big ejections of plasma. And as we zoom out further and further and further into the solar system, you can kind of get an idea of the fact that these ejections can really travel throughout the entire solar system, including reaching us if they happen to be aimed our way. Okay, so I already mentioned solar flares. That's a bright burst of light. Again, that's not just the light that you can see with your eyes. That's the entire electromagnetic spectrum, including everything from radio waves all the way up to X-rays and gamma rays. Coronal mass ejections are when the sun throws off the plasma that you can see in this video. And I'm going to play that one more time because I want to mention one more thing about how the video is made. And a lot of times these flares and ejections happen together. And so we sort of start to think of them as just one event that we'll call a solar eruption. Now, when we're studying these, fortunately, we have a lot of tools to look at the sun. There are many telescopes that are aimed at the sun, so we can get a lot of data. You're already seeing this composite of many movies from NASA spacecraft. But because the sun is so close, only 90 million miles away, we can actually do things like put spacecraft in different locations so that they can see the sun from different viewpoints. And so the last part of this video, you're actually going to see the exact same ejection, but it's the viewpoint from a spacecraft that's not located near the Earth. So here's the view of the same eruption from another viewpoint. This spacecraft is part of a set of two spacecraft called stereo, because you get that stereo view of the sun. Okay, so now we've seen what plasma ejections can do. Yeah, go ahead and ask a question if you've got one. Great question. I'll summarize the question by saying, are these colors real? These colors are chosen by the data providers to represent their data. Kind of just like, oh, you see that color green? And you're like, that's SDO green right there. So I know which instrument I'm looking at. But these particular videos, the light we're looking at is in the visible range. So you could, in theory, see this with your eyes if your eyes were a coronagraph and you had something to block out the sun, like the Earth. That's a great thing to do. If you ever get the chance to see a solar eclipse, do it. Okay, so you've already seen this video of an ejection coming out from the sun. The next thing I want to do is play all that in reverse so we can look at something at the very beginning. So we're just going to back that whole thing up, go all the way back to the sun. And what we're going to see is something that we very commonly observe in the very beginning of one of these solar eruptive events, which is a bright burst of X-rays from the start of this. Now, I haven't told you yet why those X-rays are there or how they're produced, but you can kind of get the sense already that those X-rays are probably going to have something to do with how this whole thing is kicked off in the first place. All right, with that setup, I should tell you something about what this talk is going to entail. So first, I'll talk some more about solar flares and eruptions, and especially I'll concentrate on how can these things affect us. I'll say a little bit about the methods that we're using in order to try to investigate flares and eruptions, especially the very highest energy aspects of them. And what you'll see is that a lot of the things we need to do need to be done from space. So how do we get there? I'll talk about various options you can use to try to get your telescope into space. And then, special bonus feature today only, for the last 10 minutes of the talk, I'm going to show you a video that gives you a little bit of a sense of what it's like to launch a scientific instrument into space on a scientific rocket. And this is a fairly recent experiment. We just did this last year. And so this is actually the first time that I'm showing that video in a public talk. So you all are the first audience to get to see it. I think before I start, I want to acknowledge our funding agencies. This type of work tends to be funded and addressed by a lot of different agencies because of the importance for sun's activity on society here on Earth and on space assets as well. So NASA is interested in this, the NSF funds this. We have some funding from the Air Force Office of Scientific Research, as well as various activities that are funded internally by the university as well. Okay, let's start out by addressing this question. How do solar flares and eruptions happen? Or why do they happen specifically? And not only how do they happen, but what triggers them? How do we get particles up to such high energies as we see? And what is it that determines whether an eruption is going to occur? The reason we're interested in that is because right now, if you wanted to know if there's going to be a solar flare or a plasma eruption from the sun, I could give you probabilities. I could say, yeah, maybe 50-50 that there's going to be a big flare today. That's what I would have said earlier today. But I can't tell you something like the eruption's going to happen in 1 hour, or at 2:35 p.m. today, there is a solar flare scheduled to place. No, we can't do that. We can't predict it. And we'd really like to because of the ways in which these things affect us. So we'd like to get towards not just having probabilistic predictions, but being able to say when this stuff will happen. Like your phone might have told you that that rain was going to start, right? We'd like to do that for the sun. Okay, so how did these things happen in the first place? I want to start by talking about magnetic fields. And I'm first going to start by talking about the magnetic field of the Earth, and then we'll get to the sun a little bit later. The Earth rotates mostly rigidly, not completely, but mostly. And this produces a magnetic field that is not that different from the magnetic fields you'd get if you took a bar magnet and just looked at the field that comes out from that. So this produces what I will call a relatively simple and uniform magnetic field. My fellow space physicists who study aspects of the Earth's magnetic field would really take issue with that statement. And they would raise their hands and say, it's way more complicated than that, Lindsay, but they're not here right now, so too bad. Earth is simple. But when we look at the sun, things get much more interesting. And I will, because I feel badly about having said the Earth has a simple magnetic field, I'll note that that magnetic field can get quite complex when those plasma ejections run into it and compress it. So there really is a lot of interesting physics there. But enough about the Earth. Let's talk about the sun. The sun doesn't have anything that rotates rigidly. Nothing on it is really attached to anything else except in the plasma sense. It's just a big spinning ball of plasma, and plasma is hot ionized gas. So what that means is that this whole thing doesn't need to rotate together, and the equator tends to rotate a lot more quickly than the poles do. There's different rotation speeds at different latitudes on the sun. So a spot on the sun's equator is going to come back around to find you quicker than a spot will if you go up to higher latitudes in either direction. And what this does is that it takes that kind of nice, simple dipole magnet field, and it spins it up and twists it into something that is very complicated You can build up stress this way and pressure. And eventually this produces a magnetic field that kind of has some kinks and loops in it. I like to refer to this as the ball of yarn model of the sun. If you think of this magnetic field as a ball of yarn, if you kind of wrap up your ball of yarn, like, okay, this nice, simple field, maybe that's what we start with. But then you take that ball of yarn, and then obviously your cat gets a hold of it, because that's what cats do with balls of yarn. What we have on the right is what the sun looks like after that cosmic cat has gotten a hold of it and has twisted up the magnetic field. And when that happens, there's stress and pressure in the field that needs to be relieved. That twisted up and tangled magnetic fields can cause sunspots to emerge on the surface of the sun. How many people have seen sunspots, maybe through a solar viewing telescope? Oh, great. Or with binoculars or solar eclipse glasses, something like that. Okay, great. Looks like a lot of people. This is a view of sunspots, as you can see them up here. And this image is actually in the visible range. So you could see this if your eyes were a high-powered solar telescope. So this is actually data in image from the Solar Dynamics Observatory, an instrument called the helioseismic magnetic imager. But again, it's a visual wavelength. You could see this with your eyes. Here's a new view of sunspots that is coming from a brand new solar observatory that just started taking images a few years ago. It's called the Daniel K. Inouye Solar Telescope, or DKIST, and this is located in Hawaii and funded by the NSF. So these are the highest resolution images we've ever had of sunspots, and any one of these images here is looking at just about that much, like a laser pointer beam's worth of the sunspots that you're seeing over on the left. So this is also the largest solar telescope that's ever been built, and we're starting to see data from this that is just incredible. What I take when I look at this is that even though it sort of looked like a few blobs over on the left, when you look at that in a lot of detail, you see that there's a lot of complexity. So that means there's a lot of dynamics, there's a lot of opportunity for things to change, maybe release some magnetic energy, maybe give us some clues as to how flares can start. Okay, so that magnetic field doesn't stop at what we tend to call the surface of the sun, which is this. And don't be fooled by the word surface. There's no crust of the sun. There's no actual physical surface, but we tend to call this layer the surface because it's the layer we can't see past. There's not currently any way to look further into the sun than this using a directly imaging telescope. And so we have to use a lot of models to tell what's going on underneath. But outside, it's a different story. And we have telescopes that can look at that. So let's take a look. Now, the outermost part of the sun's atmosphere, basically everything outside in the fainter parts of this, is called the corona of the sun. And earlier, Jim told you that things were maybe tens of millions of degrees at the core of the sun, and then kind of cooled off to maybe only thousands of degrees at the surface of the sun. Once you get out here to the corona, it's tens of millions of degrees again, or at least millions. And that's something we don't really understand. We suspect it's related to flares, but we don't really know how yet. Okay, and in this layer, the corona, this is where the magnetic field can become quite complex, and there's an opportunity to relieve magnetic stress and pressure by doing something called reconnecting. Now, that's just a fancy term for the magnetic field choosing a lower energy configuration and just quickly reconfiguring itself into something that is a lower energy state. In physics, things always want to get to a lower energy state. When that energy gets released, it can go into heating plasma, exciting plasma to come out of the sun, accelerating particles, and so that can cause a solar flare. Here's an image of one solar flare happening here. There's that burst of radiation I told you about. Up here, there's a solar flare, the burst of light, associated with an ejection. So here's a big old loop of plasma. That whole thing is getting tossed off of the sun, and the Earth in this image would probably just be maybe about that big or so. So it's really gigantic. I've got a movie of one more ejection to show you, so let me play that. The flare happens over here. There's that bright burst. And then you see that big ejection coming out that way, and it kind of unfurls, unwraps as it's going out. Let's watch that again, because it was really pretty. I never get tired of looking at these videos. Sometimes when Jim calls me and is like, Lindsay, why aren't you doing this? Why aren't you doing that? I tell him, I'm looking at solar videos. Do you know how pretty these are? Note that it would have been difficult to tell from this ahead of time which direction that ejection was going to go. It's not obvious that it would go off to the left, right? It could have come out kind of straight at us. So we still can't predict that very well either. So some of the things we're trying to figure out are, how does this energy get transferred exactly? What triggers the flare? If we could figure that out, maybe we could get closer to my being able to tell you at 2:35 p.m. today, there will be a gigantic solar flare. And why do some flares cause these big eruptions, whereas other flares just release a whole bunch of energy, and then the plasma cools down, everything stays at the sun, it's fine, the pressure got released. Nothing to see here, folks. We really don't understand that. In terms of the amount of energy that we're talking about, when there's a big solar eruption like this, the released energy is equivalent to about 1 trillion thermonuclear bombs. And that's released on the order of probably 10 minutes to maybe an hour, something like that. And we're in the backyard of the object that's releasing that. So I think by now you've really got a sense of why is it that I chose the sun to study. Okay, well, with that, should we care about flares at the Earth? You can tell if I put a whole slide with this title, the answer is probably yes, and we should. But let me tell you why. So just a little bit about the Sun-Earth interaction when there are big flares. I've got a NASA-produced video I want to play for you that is an artist's rendition of how this might work. This is not at all to scale, but it's meant to give you an idea of how the sun interacts with the Earth when a plasma eruption happens. So we start out with the bright flare, and then some plasma comes out from the sun. So there's the flare and the ejection. It reaches the Earth's magnetic field. There's the Earth's magnetic field. And some of that energy gets transferred into the Earth's field. And some of that energy can go down, accelerate particles that then slam into our atmosphere and light it up like one of the old TV screens. And that causes exactly, good. How many people have seen the aurora or northern lights? Oh, wow. Okay, that was what inspired you to come to this talk, wasn't it? Yeah. And I would say you've probably got another year or two near the high level of solar activity in this solar cycle to see some good aurora. Keep an eye on the space weather predictions. They'll usually give you a good idea of whether there's good prospects or not. Whether or not you can see a really lovely aurora depends on a lot of factors. So that ejection has to be aimed at the Earth, and we usually do know when that's coming by about a day or two. The magnetic field needs to be directed the right way. The ejection needs to be fast enough. So a lot of things need to happen. It does take a little bit of luck. The advice I usually give people, because they don't often think of this, is that if you're going to see the aurora, the place to see it is, if the sun is here, you want to be directly back here, because it's those particles that were coming from kind of the rear of the magnetic field that are producing this. And what that means is that your best prospects are always going to be like an hour or two from midnight. So within that range, midnight or an hour or two before and after. So you don't just need the sky to be dark. You also need to be in the right position on the Earth to see this. Solar storms have quite a bit of impact on the Earth's atmosphere. Besides causing these beautiful aurora or northern lights, they can also cause the Earth to lose up to 100 tons of atmosphere into space for a big eruption. The Earth does lose atmosphere into space every day, so don't look at me with so much alarm, but this is a large quantity, so we'd like to understand that better. These are called geomagnetic storms or solar storms. I'll probably use the terms interchangeably here. Okay, so what could the potential impacts of space weather be? Well, there was a really big geomagnetic storm and solar flare back in 1859 that we often call the Carrington event. That's up here, and the image that you're seeing here is recorded in the way that solar images were recorded at that time, which was that a scientist called Carrington used a solar telescope to project an image of the sun onto a screen, and then copied by hand, he drew what he saw. So he traced the sunspots. He also traced these bright flashes of light that he saw here, these white kernels, which were something that people had not previously seen on the sun. And that sounds just a little bit like, oh yeah, a scientist was looking at the sun and it changed. But in 1859, it was not thought that this should happen. The sun should not change quickly, gradually, sure, but there shouldn't be something dynamically changing on the sun on timescales that we could see with our eyes. So this was really a puzzling thing. And about a day later, there was a geomagnetic storm that caused gigantic effects on the Earth. It disrupted the telegraph. In fact, it supplied so much energy to the telegraph that people were shocked and caused bodily harm to them. It caused auroras to be visible in places like Singapore and Cuba. So at really, really low latitudes where you wouldn't usually see that. The lights were so bright that animals thought that it was daytime and started waking up, birds chirping, things like that. So it was a very, very large geomagnetic storm. This did have a lot of consequences for the telegraph, which was the Victorian internet, if you will. And it is thought that if something like that were to happen today, when we are much more reliant on communication satellites, GPS, power grids, things like that, it could cause a significant amount of damage. There have been times when things like that have happened. Up here, you can see the blackout region for a 1989 superstorm, geomagnetic storm, that took down a power grid in Quebec. And so it's estimated that this caused about a $6 billion impact to the economy. There's a 2000 paper that examined the United States power grid. Granted, things have changed since 2008. There have been efforts made to try to address some of this. At least by the estimates of that paper, it was thought that the entire eastern section of the US would be vulnerable to losing their power grids if a big storm like the Carrington event were to happen now. And so it's estimated that this would cause trillions of dollars in economic impact if it were going to happen. Now, before everybody goes home and can't sleep tonight, 1859 was a long time ago. Right? So I mean, it's not like these things are hitting the Earth with that kind of power regularly. This isn't a regular occurrence. We don't get it every year or every solar cycle. But 1859 is also not that long ago if you want to look at it another way. So it's the sort of thing that could happen, and it would behoove us to think about how we might be prepared for it. But don't lay awake at night worrying about this. I don't. Okay, so to be a little bit more specific about some of the impacts of space weather, I have a little more info for you on that. For one thing, here's one more view of an ejection. That went fast, so I'm going to play it again. This is an ejection from the sun that's coming right at this telescope. So watch that. You see the ejection from the sun, and then you immediately see the camera just go crazy. That looks like noise or static or something like that. What that is high energy particles from the solar flare that are hitting the camera and causing it essentially to not work well anymore. So this can be a big vulnerability of satellites. There have been cases of satellite instruments that have been essentially taken out, made dysfunctional, don't work anymore. After a big geomagnetic storm, GPS devices are vulnerable to this too, as well as everything that depend on those systems. Anywhere you've got a big metal conductor on Earth is vulnerable to induced currents in that conductor. And so that applies to things like oil and gas pipelines. There are some things that you can do to make those pipelines a little less vulnerable, though. They're not easy, but it can be done. Things like aircraft communication, actually any sort of radio communication. This is one that I worry about a lot because this can happen as soon as the solar flare happens, not just when that big geomagnetic storm arrives a day later or so, and that means we really don't have warning of that happening. There have been cases of things like radio communication blackouts at times when there are hurricane relief efforts at work, and that means all of a sudden people's main ways of coordinating that relief just disappears with no notice. Human spaceflight. This is especially relevant as we start to go to more and more places in the solar system. Certainly when one of these big ejections is coming our way, you would want to make sure to have your astronauts as shielded as they can be, or maybe even a different place if you have propulsion that can actually get you out of there. So this will become more and more relevant in the coming decades. I already mentioned the power grid. This is one of the impacts that would probably affect us most directly and possibly for a long time. It's the large transformers between different sections of the power grid that tend to be the real vulnerable places here. And then pretty much everything that depends on those other systems that I already mentioned, like our water supply, agriculture. I've had people at the University of Minnesota who work in agriculture come talk to me about space weather impacts because there have been impacts whenever GPS goes out. Okay, so it turns out the sun can do quite a bit. But what color is it? Does anybody know? Go ahead, shout out some possibilities.
White.
Ooh, okay, I'm getting yellow, orange, white, green. I've got a green. This is a great question to ask a crowd because you can't get this question wrong. All of the answers are correct. Yeah, it was a trick one. I don't usually do that when I'm teaching my physics class, just in case you're thinking about that, but here I'll do that. So when my 6-year-old son draws a scene involving the sun, he usually chooses a yellow crayon. That would be right. That's where the sun puts out the most photons, the most parcels of light is at a yellow wavelength. But if he chooses a green crayon or purple crayon or blue crayon, that's right too, because those colors are in the sun. If he had an X-ray crayon, which sounds sort of terrifying, and I'm glad he doesn't, but if he did, and he chose to use his X-ray or gamma ray crayon, he would also be correct because those wavelengths are also coming from the sun. A lot of different wavelengths in the sun, and depending on what it is that you want to see, you can choose different wavelengths that will show you what you want to look at. Here's an example using images from the Solar Dynamics Observatory. Let me show you what we have here. So down here, this is a visible wavelength. It's the same one where I showed you the sunspots earlier. And then up here are ultraviolet wavelengths. You're also seeing some material that's pretty close to the surface of the sun here, kind of like this one, but a little higher up. And then all of these are extreme ultraviolet wavelengths, which is just like ultraviolet, but even more so. So it's higher energy ultraviolet. And each of these wavelengths is tuned to be sensitive to a very specific temperature in the sun's corona. And that means it can show us what are the structures and the dynamics that are going on at that specific temperature. That means as a scientist looking at this data, and by the way, all of you as scientists can look at all of this data. All of the data that I'm showing here is publicly available, and you can just pull it up on your computer. In fact, if you go to helioviewer.org, you can get these kinds of images, full sun, several different filters from about probably a half hour ago. That's usually how quickly they put them up there. So you can find out what's going on the sun almost now. Okay, so I want to play this video for you. In all of these filters, the telescope takes full sun images, but the person who made this video kind of sliced it into pie slices so we can see. And what I want you to pay attention to is how the structure on the sun changes every time it gets to another filter. Okay, so we're letting our filter wheel kind of just rotate across the sun here. As soon as we got here, we started seeing this hot stuff in the corona. But then sometimes when we go between filters, features just show up or completely disappear when they get over here. And again, that's because each of these filters is looking at a different temperature. And so a lot of what scientists who study the sun do is make choices about which wavelengths we want to look at and figure out how to put those wavelengths together to tell the most complete story we can about what's going on the sun. Okay, so far the message is there's a lot of different data we have for the sun. And because the sun is so important for space weather, we really do have a lot of data. There are many telescopes that are trained at the sun. So you can get this, you can analyze it, but you need to make intelligent choices about what you want to look at if we're going to be able to answer some of the questions I mentioned earlier. So I always say, if you want to know about the highest energy stuff that happens at the sun, these gigantic flares and ejections, use the highest energy photons, highest energy light that you can. And that's X-rays and gamma rays. How do you get this? Well, you can get X-rays through a process called Bremsstrahlung, and I will never make you spell that, I promise. You don't even have to remember it. There's not going to be a quiz later. But what this emission is when you have energetic charged particles traveling through, some sort of plasma. They run into protons, and every time they run into things, they change their direction and speed a little bit. Jim told you earlier at the very start of the talk that counts as an acceleration. That means that you can emit some energy. And in this case, sometimes that energy is emitted as X-rays. So that's a great way to get X-rays. X-rays are really high energy. That's why they're used for medical images. They tend to either just go right through your body, or they can get absorbed in your body. And looking at the differences between those can tell a doctor or technician what they're looking at inside your body. Okay, when we make X-ray images of the sun, what we tend to see is this. This is now a solar flare as viewed in X-rays. Do not try to view the sun in X-rays at home. But what we typically see is this. We see a loop with very, very hot plasma for this flare. It's probably about 20 to 30 million degrees. And then we also see places where energized particles are just slamming into the solar surface like that. So we know they're there, but we don't really know how they get there. And this is the kind of stuff we would like to investigate in a lot more detail if we're going to figure out how do solar flares happen? How does that energy get transferred? Why do some flares produce ejections, others don't? This is the wavelength that we primarily need to be looking at. Okay, so we've come a long ways. We've figured out what we want to observe, and we know something about what we might learn by observing that. So what's the catch? It's this little thing called the Earth's atmosphere. This graphic gives you an idea of what kind of light can get through the atmosphere. Again, there's a lot of different kinds of light. So there's radio waves, microwave waves, infrared, visible light. There's ultraviolet, X-rays, and gamma rays. Not all of those can get through. So there's kind of a window here in the radio. Radio waves can get down to the ground. That's how we communicate with satellites. There's a window up here, of course, for visible light. Visible light can get through our atmosphere. I think we all have experimental verification of that one. And then you can get maybe a little bit of infrared, but once we get up here into the ultraviolet, X-rays, gamma rays, the atmosphere does a really good job of absorbing those. And frankly, that's a good thing. If that weren't the case, then we probably wouldn't be here, because I don't know about you all, but I don't want to be blasted by X-rays from the sun all the time, no matter how much I want to measure those. In my own opinion, I would have made this part of the atmosphere look a little more transparent to these wavelengths, because high energy stuff can get a little bit of the ways through the atmosphere, but not crucially all the way to the ground. Okay, so this is good. We don't want high energy X-rays hitting us all the time. But if your job is to do X-ray observations of the sun, I gotta tell you, this is a real downer, because this means I can't just build a telescope and put it on the roof of this building. I need to find some sort of way to get to space. So to sum up so far, telescopes can target different wavelengths of light on the sun, from radio all the way to gamma rays, and choose the wavelength that tells you the information that you want to know about what's happening. But if that wavelength happens to be one that can't get through the Earth's atmosphere, then you're going to have to put your scientific instrument in space. And how the heck do you do that is going to be the next topic of the talk. Okay, how do you get to space? And I don't mean you personally. I mean, There are ways to get to space. You could be an astronaut. You could go for a ride on a space tourism rocket. That's a thing now that people can really do. But I don't mean you personally. I'm not going to talk about those pathways here. What I really mean is, how do you get your scientific instrument, which I really view as part of me, to space? And now I'm just going to kind of rapid fire tell you a few of the ways that we can do this. And I should start by saying that, I'm really talking about how do you get your stuff to space if you don't just randomly have a gigantic rocket that can launch a huge spacecraft into orbit around the Earth, or better yet, the sun. I mean, if you do have one of those at home, then come talk to me about that, because I definitely want to chat. But I'm assuming that we don't have that. I don't have that. And so we need to get a little bit more creative. Here's one way you could do it. You could fly your instrument into space on a NASA sounding rocket. Now, sounding here means in the sense of sounding a discovery space, like making new discoveries. And these are relatively small, in the NASA sense, rockets that can send a payload basically straight up into space, but without enough speed to escape the planet or go into orbit. What these are typically used for is to test new technologies. So you get some of the most groundbreaking new discoveries come from these experiments, because it's the latest and greatest technology, really cutting edge. They're much lower cost than getting a gigantic rocket to launch a big spacecraft. And because of the aspects I already mentioned, there are lots of opportunities for student and early career scientist and engineer involvement on projects like this. So if we are talking about a big NASA flagship spacecraft that costs $1 billion, a student is never going to be able to solder something on that. Everything is going to be done by certified NASA technicians who have established over and over that they know how to do this. But when we're talking about projects like this, something breaks, student solders it together. It's just a natural part of the project, and is actually one of the most exciting parts. Okay, so we've got one route to space. We can use a small rocket to launch a payload straight up. If you launch something straight up, what happens to it? It comes back down. It sure does. And so this can get you to space for about 5 to 6 minutes. So it gets something to space, but it doesn't leave it there for very long. If you're going to use this as an opportunity to do science, you're going to have to be very strategic about how you time this and what it is that you scope your project to be able to do. And the University of Minnesota has launched a lot of these. I'm going to talk about one payload in particular later in the talk, so I'll kind of defer more sounding rockets stuff till then. But really, the University of Minnesota has done sounding rockets for several decades now. Okay, so 5 to 6 minutes isn't enough for you, you say? You want more data than that? We always want more data. Maybe you could put your experiment on a balloon and send it up. There are lots of high-altitude NASA balloons that launch each year in various locations. And these high-altitude balloons can carry a payload to about 50 kilometers. That's about maybe something above 100,000 feet, so over 3 times the height that a passenger jet might fly at. So it's pretty high up. If you're in one of those wavelengths that can just barely eke through part of the atmosphere, that might be enough for you. And then you could really get a lot more observing time, maybe a day, maybe a week, month, something like that. These types of projects are also frequently used to test out brand new technology and to train students. So they tend to be in that category of lots of early career involvement. So you can get a longer observing time, but you're not quite in space. I also want to point out that this platform is really relevant to one of the questions that I most frequently get from children, which is a really, really important question. And it's, what happens to my helium balloon if I let it go? Do you all know the answer to this? There's several people who, oh yes, we've got some answers to it. Anybody want to take a stab at it? One more time. Very good. That's a good one. Was there other answers over here? Anyone else want to give another explanation? Maybe you? It'll pop. That's a good one too. If it gets high enough. How about you? You guys know all the physics already. This is fantastic. Nice job. There's another answer? That's another possibility. That can exactly happen. And we would like this platform to be in that category and not that category, but you two are right about yours as well. Okay, any other descriptions? These are all correct. These are all sounding really good. Okay, I am pleased to know that people know so much physics here. So that's exactly right. If you let go of a helium balloon, it's going to go up because the air pressure is lower, higher up. That balloon is going to expand. Now, usually with kind of a small helium balloon, the balloon material itself isn't going to be able to sustain that expansion. So if that's the case, it pops exactly like you said it was going to. But if your balloon is made out of materials like this, especially some of the materials that were developed at the University of Minnesota in the early days of ballooning, then what happens instead is that eventually you reach a place where you stop going up. And that's because the weight of the payload is equivalent to the weight of the air that you're displacing. But you don't pop because your balloon can sustain that kind of pressure. And then you don't really go too much up, too much down, except as part of the day-night cycle. And the goal is that you just kind of drift at that altitude, wherever the winds are going to take you. Okay, so don't say you didn't learn anything at this talk, because we learned a very important thing, which is what happens to all of those helium balloons that my son has let go over the past 4-ish years. I want to point out that Minnesota is doing some high altitude balloons, but this isn't new for us. Minnesota actually has a really long history in high altitude balloons. And here's a photo of a balloon getting ready for flight during the International Geophysical Year of 1957 to 1958. During that year, Minnesota flew 85 balloons that usually stayed up for about a day. So they did pretty good. And flew them in various locations. Most of them were flown right here from Minneapolis, from university grounds, which nobody lets me do anymore, but they really should. But others of the balloons were flown from Alaska, Canada, more equatorial regions like Guam, Cuba. So 85 of these over the course of the year. It was really an impressive achievement. And they learned a lot about cosmic rays and about solar flares. So a group from the University of Minnesota, led by Peterson, Winkler, and Ed Nye, actually produced the very first observation of what I'll call an X-ray / gamma ray flare. The title of the paper says it's gamma rays, but whatever, we can have slight disagreements about that. So this was the very first high energy solar flare observation, and it was a University of Minnesota project. So you see why I had to leave Berkeley and come here, because this is where the exciting stuff is happening. Okay, nowadays, because nobody will let me do this from Minneapolis, we have to find somewhere else to do it. And many NASA high altitude balloons fly from Antarctica. So we've actually got an experiment that's heading there in December 2026. It's called the IMPISH experiment, and it's going to measure X-rays from solar flares with better timing resolution than anybody has ever done before. This is a piggyback payload, which means it's flying on top of a larger payload. And this is the flight path that that larger payload took the last time it flew. This is McMurdo Station down here. And then each of these numbers is a day. So it kind of circled around the continent. They had to cut it down around here because it was starting to come too low in altitude. But we're actually hoping that maybe this time it'll go all the way around and we can get another week or so of observations too. This project is led, designed, built, tested, and will be flown entirely by grad students, almost entirely by grad students. So they're really doing a lot here. And those grad students, in addition to doing lots of great work on this project, also hold the prize in my lab for using the most equipment in our lab at the same time. I mean, really, the experiment is just these few electronics boards down here and the detector here. And yet somehow they managed to use almost every piece of equipment in the lab at once. So I think that's an impressive achievement that deserves recognition. Okay, so you say a sounding rocket was too short for you. and you like the balloon, but it doesn't get up high enough, because if that balloon went up higher, then we already learned it would pop. So maybe you can build a satellite, but we'll just make it a small one. There's a class of small satellites called CubeSats that are about the size of a shoebox, some a little larger, some a little bit smaller than that. And these ones are often launched as piggyback payloads, there's that term again, on larger missions or large rockets that are putting a large asset into space. So the way this works is that if a government agency or a company is launching something big, let's say a communications satellite or a scientific satellite or something like that, they might be able to take a few extra kilograms, or maybe a few extra kilograms, and actually get a ride to space for some missions that are essentially being like, hey, can I get a ride? And so that's actually a pretty common way to get to space for small payloads that can be built by, for example, university teams with a lot of student involvement. And again, this really raises what you can do with projects like this, because you can involve students in them, but you do need to figure out what can be done with this kind of size constraint. If you're wondering how you do the part where you stick out your thumb and ask for a ride, NASA does have the CubeSat Launch Initiative to kind of help with this. So they're the interface between, okay, here are all the organizations that are putting a payload in space that might have some extra launch capacity. Here are the university and company teams that want to put a CubeSat there, and they kind of do the lining up for us. It's not free, but it does cost a lot less than a dedicated rocket. Okay, I mentioned that we have a lot of student involvement in projects like this. And at our university, this is mostly through the Small Satellite Research Laboratory. This is a multi-departmental team. It's led by this department, the Physics and Astronomy School, and also Aerospace Engineering. It's a collaboration, but we have students from across the entire College of Science and Engineering. There are a few dozen undergrads that usually work on this every semester, with mentoring from grad students and from scientists and engineers who are staff at the university. And they're currently working on one CubeSat mission called the IMPRESS mission that is going to measure X-rays from solar flares. And here's just a few photos of the team at work building things. You can kind of get a sense of, it's not the easiest thing to fit everything into a shoebox size. I mean, it's still a whole satellite. You have to have solar panels, power, communications. You have to be able to control where you're pointed, because we do need to look at the sun, not look some other direction. So it's a lot to fit in a little package, but it's a lot of fun to do as well. Those same students are also working on a project that is not a standalone satellite, but we'll go here. Here's another place that you can put your scientific instrument, the International Space Station. The Columbus module, which is located over here, has several platforms where experiments can be installed. A lot of these are Department of Defense experiments. And like I mentioned, the Air Force is interested in space weather and its impacts on Earth and Earth assets. So there is a lot of interest in this. This is a place where experiments can be hosted for about a year or so. And here, the space station provides the power and gets your data to the ground. So in some ways, there's kind of less to do there, but still plenty of challenges. So we're working on an instrument that will be mounted in approximately that location in about 2027. And this experiment is also completely designed and built by undergrads. Okay, I'm just going to finish up with the last bonus feature that I mentioned before. So I think I'll probably go over by a few minutes, but not a lot. I promise you, it'll be worth it. Because the last part of this talk is entitled, What's It Like to Launch a Scientific Rocket? So what's it like to launch a rocket with a scientific instrument on board? Any guesses? What adjectives come to mind? Pressure. That's a good one. Yeah. Weight is a good one. Yeah. Boring. By the end of this presentation, I bet you'll have changed your mind. Any other suggestions? Fire. There's a lot of that, hopefully on the right things and not the wrong things. Yeah. Stressful, accurate. Yep, right on with that one. Any others? Go ahead. Long? Yeah, it's a long road to get there. And then the launch is really short. And you're like, what just happened? Yeah? Fire extinguisher safety is very important on the launch rail. I'm loving these. Yeah. A lot of G-force as well. And your scientific experiment has to be designed in order to sustain that. Something that goes right along with that stressful we heard earlier, right? Yeah. Yeah? Loud. It is loud. It's loud, but it's also all the senses because you see it happen. You see the launch, and then the pressure wave hits you later. And somehow I always forget that that's coming. And I was like, whoa, pressure wave. Okay, so everybody is right about this. I asked you another question where all answers are correct except for boring. For me, the adjectives or adverbs that I wrote down are painstaking, frustrating. So there's a lot that needs to be done. Exciting, nerve-wracking, and thrilling. So some of these mirror some of the things that you all correctly intuited. And I should have asked, has anybody seen a rocket launch? A big rocket, small rocket, any kind of rocket? Good. On TV? Yeah. So those, okay, good. We've got some people who have seen rockets. Anybody want to mention what rocket they saw? You launched a rocket, even better. So you know all of this already. Perfect. Okay, good. Can I put a scientific telescope on that? I'm just kidding. I won't try to get an instrument onto your rocket. Okay, great. I'm glad to hear that people have seen these. And I think every kind of launch, whether it's a big shuttle launch, okay, they don't do that anymore, but they launch big stuff. Whether it's a rocket club launch, we have a really, really avid and good rocket team here at the University of Minnesota. Whether it's a sounding rocket, they're all really thrilling and painstaking and frustrating and nerve-wracking. Okay, so the rocket that I'm going to tell you about was launched in April of 2024, so just over a year ago. And this was NASA's very first attempt to try to launch scientific sounding rockets during a solar flare. You might recall from earlier that sounding rocket flights aren't very long, 5 to 6 minutes of observation. So you really have to time it right. And you might remember from even earlier in the talk that we still don't know how to predict when solar flares are happening. So that means you have to be like ready to go. Like, should I launch now? How about now? Yes? No? Go. Okay. So we convinced NASA that this should be possible. They said yes. Unbelievably, that still shocks me a little bit. And they let us launch not one, but 2 rockets during the same solar flare. And so we did that last April, not this April, but the one before that. And the missions were both successful. I'm going to not talk too much about the hardware for the sake of time. Our payload included 7 X-ray telescopes in different wavelengths. And we tried to answer questions like, how does energy release during solar flares? How do particles get to high energies? And what do they do with all of that energy after they're excited? So in this image, you can see the mirrors on this side. These are X-ray mirrors and then X-ray cameras down here. And here's a few images from putting the experiment together. This is at an integration facility in New Mexico. After this, we took the payload, both payloads, to Alaska, where we flew this from a University of Alaska rocket range. So you can kind of get a sense of what we're doing. There's the telescopes there. Cameras are here. It's hard to see too much there. And it's starting to look a little more rocket-like as we put it together here. The next photo is just gratuitous because my family came out to visit me while I was there. And so my then 5-year-old son got to visit a missile range. And of course, his favorite part was the safety equipment that we use to work with the cryogenic fluids. So that's obviously the most exciting thing at a rocket range. There's a question over here. Oh, that's a good question. So I am here, but this is me with whatever hair color I had in 2024. Who can even remember anymore? It's hard to keep track of me. Also, as a side note, we got the camera field of view just a little bit wrong here because right here is a University of Minnesota flag. And whoever took this photo, I need to have a talk with about that. And the reason that flag is there is because Minnesota flies sounding rockets and has for some time. Okay, so let's move on to the launch campaign. Like I said, we successfully flew in 2024. We had to respond quickly to a flare, so we had a countdown that was only 3 minutes long. Actually, we had a much longer countdown, but then we stopped the clock exactly at 3 minutes and held it there and waited. The launch occurred on day 8 of a 9-day campaign. Those of you who are very good at math will note that that was the second to last day of the campaign. Who was it who said stressful earlier? Yeah, you nailed it. The launches were separated by 1 minute, and we each got 6 minutes of observation. And the flare we observed was a big, beautiful one. That was exactly what we wanted. Now, how did we know when to launch? We built a set of tools to do this. I'm showing you this because this will show up in the video I'm going to show you. Don't worry much about all of these plots. These are showing X-ray flux as monitored by a NOAA spacecraft and also ultraviolet emission that's monitored by a NASA spacecraft. All we really need to know here is that when the lines go up, a solar flare has started. And if they kind of level off, maybe we should worry about things because that might indicate that we could miss this solar flare. Remember, 3-minute countdown, and then it's still going to take us 2 minutes to get up to space. And if things start trending down, then we should really call the whole thing off because that might mean that we're missing it. We developed this. We had personnel for flare monitoring. We developed a lot of scientific intuition for this, and we also had a necessary ingredient. Good luck. Okay, with that, I'm going to play this video and let me show you what's in it. Here's the screens I already introduced to you. Here's that countdown clock. So it's been mostly sitting at 3 minutes for 8 days now, but you will see it change. Here's a view of the launch site. It's hard for me to view from this angle, but here is the first rocket. That's FOXSI, that's ours. And here is the second rocket. That one's called HI-C. The one on the left is going to go first, and it will be obvious when that's going to happen. And then later on, you'll get a view of our data up here in the white space up there. Okay, so let's roll the tape. And this is a record of the communications that we were having during the countdown as recorded on the headsets we were wearing. I'll give a little commentary as we go.
Dr. Sam, we are monitoring a small increase in solar flux.
Because notice the lines are going up. So that means, hey, something's happening. We're not launching yet, but we're going to keep an eye on it.
Okay, thank you. All right, we are at around our trouble.
Still at 3 minutes.
Go ahead and swing to about 355. See if that clears us up and then swing back. Are we going to be at
something started blinking. That's a good sign.
Launch?
The lines are going
This
up.
is the FOXSI we would like to pick up the count. Copy that.
Notice that NASA did not say, finally. I know they wanted to. So at this point, the scientists are monitoring these lines to try to see, is this going to continue going up or is it going to come back down? Because we cannot miss this. This is our one chance. And if we launch, that's it. That's over.
PLC 1 check 225.
ACS
2 check 228.
Sorry, it's loud. You're going to hear people checking off their checklist items. So we're making sure.
CUS 1 verified 221000. CUS 2 check 223. PLC 1 check 231 232. PLC 2 check 226. ATM 1 check 244.
ACS 1 check 222.
Now notice that some of these things are starting to flatten. For those who are familiar with calculus, this one is showing you the derivatives. So here's the fluxes, here's the derivatives. Things are starting to flatten a little bit, but the fluxes are still going up. We need to decide if we want this flare or not. And what you're going to hear is that we decide to hold and take more time to think about it.
ACS 2 checks 224. Okay, experiment check 237.
That was a postdoc. It works here.
Check 229 230. CUS 1 check 227. 2S1, can we get 221?
Can I get hold
243.
hold the clock in 1 minute?
Of saying stop the clock. We're going to hold.
Gonna hold it
We're going
1
to think
minute.
about this. We hold for a couple minutes while we watch the flux. At this point, we've realized we're not going to get.
Dan, we would like to pick up the count still target echo. Copy that? Let's pick it up. At
We're
the
going to
top so we
miss
can catch
the
it.
peak of the flare, but it looks like the flare is going to last long enough for us to be
1
able to
minute.
get up there.
Launch number 1, T0, 22, 12, 00.
Next, you're going to
Launch
hear
number
them
2,
do their
T0,
go statuses, which
22,
means they go through all of the
13,
systems and make sure everyone's
All
ready.
stations, this is go.
This is the
Hold
fun
for
part.
launch. Programmer,
Go.
surveillance.
Go.
Rick,
Go.
LO1,
Go.
LO2,
Go.
PTM1,
Go.
PLC1,
Go.
ACS1,
Go.
NFORCE1,
Go.
CUS1,
Go.
FOXSI experiment,
Go.
PTM2,
Go.
PLC2,
Go.
ACS2,
Go.
NFORCE2,
Go.
CUS2,
Sweaty
Go.
hands.
IC experiment,
Go.
Anyone else?
FOXCPI, go, ICPI, go, MM,
Go.
poker,
Poker does not say go.
standing by for poker.
The poker flat, the range, is at this point unsure of whether there is a truck on the local highway. They've got roadblocks, but due to one poor walkie-talkie communication, they are not sure whether the truck stopped. And you can't launch if somebody might be in the.
ACS to check
Excursion range.
250.
We are held with 23 seconds left on the clock. And when we pick it up again, you're going to hear
Programmer,
me
please take us back to
pause
30
before I
seconds.
say go, because we need to decide if we still want this flare.
I'll pick back up with the FOXCPI for go polls once we get the hazard area clear. Other stations report red if you turn red.
So we're now madly looking at the data saying, should we still do this? Should we still do this?
Programmer, please pick it up on the half.
Programmer copies.
FOXCPI, go.
30.
High CPI, go. MM,
Go.
poker, go. CMS, go.
The
RSO,
truck is
go.
going now.
PD, go. Check 246.
22, 13, 00. UT0 for launch number 2, 22,
ACS
4500.
ACS 2 checks 252. 8, 7, 6, 5, 4, 3, 2, 1, 0. Lanyard strip.
There's the first launch. We've got
Plus 10.
about 1:40 to get up to space.
Power check. Plus 20. Black land ignition. TM is on our track. Motor pressure.
High CPI, still go for science.
That's the PI of the other experiment.
30.
She says it's still good. Now they need to make sure our launch motor is cleared and has successfully fallen away before they launch the second one. Listen
Minus
for good
20.
vehicle.
Arthur, good vehicle.
Good vehicle.
ACS 2259. Minus 10, 9, 8, 7. Arthur, go. 6, 5, 4, 3, 2, 1, 0.
Here's the second rocket.
Lanyard full. Launch IC, launch taxi. IC D-spin. Motor set. Plus 10.
That launch also goes successfully, so everything's okay with those. By now you've got our data displays up here. You're not going to see anything yet, but when we get to about 1:45, you'll start to see some stuff. Yeah. Oh, that's a good question. We got really bored during some of those 8 days of waiting. So we found all sorts of ways to amuse ourselves, including by saying hi to mom, which I think is great.
The second rocket, was that intentional?
It was intentionally at a minute. So it was included in the list of countdown items. And if something had been non-nominal, they could have held that later. But that was intended that they would be exactly 1 minute apart.
1 minute. ICD descent.
Okay, I think the video is going to stop here, and we'll kind of stop on this screen. What you're seeing on our data display right now is our solar flare right in the middle of all of the displays. The displays look pretty noisy, and if you work at all with cameras, you're like, oh, why is there all that noise there? That's very easy to filter out. We do that in our post-processing. We don't filter anything during the flight because it is way too easy to accidentally filter out the thing you're trying to look at. But this thing right in the middle of our display is our solar flare. And I think I'll probably end by just showing you a nicer view of it, which is here. This is what it looks like after our data processing. This is data from the first payload, the FOXSI rocket. This is showing you X-rays. That's our flare happening. And this is data from the second rocket called HI-C, which is an extremely high resolution, extreme ultraviolet imager. Yeah, there's a question over here. That was software that we wrote in order to monitor what was happening on the sun. So you might notice that it kind of started flashing right around the time when I was like, hey guys, start the clock. That wasn't a coincidence. As soon as we got that trigger, we had previously done the math to know exactly what our probabilities would be of success. So we looked back at, I kid you not, 10,000 previous solar flares to try to see, okay, if you see this particular trigger, what are the chances that this will be successful? So yeah, that was a button that we put there to kind of tell us that. I don't know who was next. We are just naturally going into the Q&A. Is that okay, Jim? Or
Let me just wrap up.
okay, Jim's got a couple things he wants to say. That's my last slide.
The question and answer, but I just want to first advertise next week's talk by Professor Patrick Kelly, who will talk about gravitational lens. Instead of looking at bright suns, looking at things we can't even see, and we can see them through the way that they affect space-time and affect other things that we can see. So that's gravitational lensing in dark matter. And one of the things that I love about Professor Glesener's work is the number of undergraduates. I mean, it's just like amazing how many of them are working entirely on these projects. And even if they had missed the solar flare, the project would have been successful because its outcomes would have been trained scientists.
Yeah.
The only way to teach someone, to train someone to be a research scientist is to have them do scientific research. In all history, no one's ever gotten the driver's license by only taking a written exam. These are behind the wheel training, and that's what she provides amazingly well. The point I wanted to make here is in 1903, Orville and Wilbur Wright, out of a bicycle shop in Dayton, Ohio, designed, built, and then at Kitty Hawk, North Carolina, tested the first aircraft. 66 years later, Neil Armstrong walked on the moon. And the first Boeing 747 is launched. That's not done by two guys in a bicycle shop. The outcome of the research that we've seen all in this series and will continue to see is involves the students here, and it's part of the teaching. The research that we do is also part of teaching people how to do research. And you see here, just someone asked, where is
I'm at the top in that one.
wait, which one?
Was I blonde that time too? Yeah. Okay, that was a blonde
Is
year.
that you?
Yeah,
Oh.
at the top.
Okay. So anyway, as I said last time, to learn more about the research, go to the School of Physics and Astronomy's website, and to support the School of Physics and Astronomy, here's a QR code. And now, questions and answers.